has a galvanometer which measures tiny amounts of current, in this example up to 10 microamperes, and she wants to use it in an experiment to measure voltages up to 10 volts. Now she doesn't want to buy a voltmeter, so she comes to you and asks you, hey, can you make this galvanometer somehow measure up to 10 volts? And being a physics enthusiast, you say, sure, I can do that. I can, change things inside, but it'll cost you a little bit. It might cost you about 300 rupees. And she will say, yeah, cool, I will give you that, no worries. And so the question we want to try and answer in this video is, how do you take a galvanometer and convert it into a voltmeter to measure up to some specific amount of voltage? Now, before we begin, the first question you might be having in your mind is, hey, this is a current measuring device. How can we measure voltages across it? How does that work? Well, I have one word for you, Ohm's Law. Well, actually that's two words, but what I'm trying to say is, if you know the current across, current flowing through any device, then from Ohm's Law, we know the voltage across that equals I times R. Which means if I knew what the resistance of this galvanometer is, then knowing the current, I know what the voltage across it is. So for example, let's say the resistance of this galvanometer was, just for the sake of example, let's say it was 100 ohms. And if we didn't know, we could calculate it. So that's not a big problem. We can measure it for it. That's not a big problem. So if we knew the resistance was, say, 100 ohms, and let's say when we're using this galvanometer, let's say the galvanometer deflection shows 10 microamperes. Let's say this is the situation right now. Then I know the voltage across the galvanometer, we just call it as VG or something, VG, okay. That voltage across the galvanometer, maximum voltage, you can think of it over here, that would be the current through the galvanometer, which is 10 microamperes, times the resistance of the galvanometer, which is 100 ohms. And that would be, in this example at least, 1000 microvolt, or 1 millivolt. So you see, I can think of this as a very, very tiny voltmeter. And I can just change the sticker and I can say, look, this is a millivoltmeter. All right. So even though we don't think of it that way, galvanometers can also be thought of as tiny voltage measuring devices as well. Excellent. So that means I already have a tiny voltmeter which can measure up to 1 millivolts. I just have to change the sticker. All right. So the now question is, how do I make this tiny voltmeter measure up to 10 volts? That's the question we want to try and answer. This can measure only up to a millivolt. If I put more than that, there'll be more current flowing through and this will break. So how do I make this measure up to 10 volts? How do I do that? Another way to put this question is, how do I ensure that when I put 10 volts across this galvanometer, that's when the deflection shows 10? Because if I could achieve that, then I could just change the sticker, put it to V volts, and I'm done. Then when I put, say, 5 volts across this is a linear devices. Galvanometers are linear devices. So when I put 5 volts across this, automatically the deflection will be half of this and it will show 5. Okay? And of course, if we were extending it to, say, 100 volts, I could use the same logic. I could just put 100 here and 50 here. And so my big question is, when I put 10 volts across it, I want the deflection to show maximum 10. How do I do that? Well, we already know that in order for this galvanometer to show deflection of 10, I need 1 millivolt across it. Not 10, but I need 1 millivolt across it. Which means our question becomes, how do I ensure that when I put 10 volts across this device, somehow the galvanometer only really gets 1 millivolt? Did you get the question? I'll repeat. When I put 10 volts across it, I want to make sure the galvanometer only gets 1 millivolt. In other words, the rest of this voltage should get dropped somewhere else. Ooh, you see where we're going with this? If you want the rest of the voltage to get dropped somewhere else, we need to attach something in series with it. So here's how I'm thinking. If I could attach something in series with it and ensure that when I put 10 volts across it, only 1 millivolt comes across the galvanometer and the rest of the voltage comes across, say, whatever I'm attaching over here, rest of the voltage, which is 10 volt minus 1 millivolt, should come across this device, then I'm done. Because then what I could do is I could just put a box around it so that my friend doesn't see what I did, okay? And I can give this box to her, and as far as she's concerned, this is a voltmeter. When you put 10 volts across this entire device, it'll show 10. But you and I know that in reality, when you do that, 1 millivolt comes across this, and that's why it's showing 10. So we need to add something in series to convert it into a voltmeter. But now comes that question. What should I add something? What should I add over here? And how should I think about it? Like, what should I measure about that material that I'm adding? So it's an open question. I want you to think a little bit about it. What do you think, how would you go ahead with this? What should I add, and what measurement should I be worried about over here? All right, here's how I'm thinking. Since I want the voltage, the 10 volts to split up, so some voltage comes here and the rest of the voltage gets dropped over here. And since these are in series, current is the same. So the voltage that they get really depends only on the resistance. So I really only care about the resistance of that material. So I might also just add some resistance over here. So now our question changes, and our question now becomes, the final question that we have about design is, what resistance we should add in series with this such that when I apply 10 volts across it, 10 minus 1 millivolt comes across this resistor. And you need to add a very specific resistance, because think about it, if you add a very low resistance, then a very low voltage gets dropped across this, and rest of the voltage will drop across this, and this galvanometer will blow up. You don't want that. You also don't want very high resistance. If you put 1 billion ohms, let's say, then all the voltage will get dropped across this, nothing will get dropped, and your galvanometer will not read anything. So that's also bad. So we need to add a very specific resistance so that the voltage gets divided precisely like this. And so now this is a more fundamental electricity question. How do I calculate what resistance should I put over here? Again, I'll give you a clue, Ohm's Law. Can you think about the situation from Ohm's Law perspective and figure out how to calculate the value of R? Go ahead, give it a try. Pause the video and give this a shot. All right, so here's how I'm thinking. I already know the voltage across this resistor is supposed to be this much. And I also know the current that's supposed to be. When the voltage is this much, the current has to be 10 microamperes, right? That's the current that's flowing through the galvanometer. It's showing 10, it's really 10 microamperes, right? And so I know both voltage and current, I can find the resistance. So the required resistance is voltage, that is 10 volt minus 1 millivolt, divided by the current, which is this much, 10 microamperes. That's the current. And if I substitute, I get my answer. And that would be the resistance to be attached over here. And if I do a quick calculation, I can neglect this 1 millivolt in the numerator because it's very small compared to the 10 volts. And if you divide this by this, then the 10 cancels, you get 1 divided by a micro, and that's about 10 to the power 6, right? That's about 1 million. So you'll have to add 1 million ohms of resistance in series with this. And this immediately tells you that voltmeters tend to have very high resistances, as you can see, because we want a lot of voltage to get dropped across that series resistance. But anyways, conceptually, we now understand that a high resistance has to be added in series with the galvanometer. And once we do that, then we can just package it like this so that your friend doesn't see what we did. And we can tell your friend that, hey, we did a lot of work, took a lot of time and effort, and then we'll get paid our 300 rupees and we would have made a profit because resistors only cost, 10 or 20 rupees. Wonderful, isn't it? Because as far as she's concerned, this is a voltmeter. If she were to put, I don't know, maybe say 2 volts across this, or let's say 1 volt across this, 10 times smaller, then automatically this would be 10 times smaller, this would be 10 times smaller, the current would be 10 times smaller because the resistance doesn't change, the current would be 10 times smaller, the deflection would be 10 times smaller, and it would show 1 volt. So you see, this is, as far as she's concerned, a voltmeter that can measure up to 10 volts. Finally, if you are wondering, what should be in general, what is the general expression for the resistance that needs to be added to convert a galvanometer into a voltmeter, we can just look at this and figure out. See, 10 volt was the voltage up to which we were extending. So this is the voltage to which you need to extend your galvanometer's range to. Minus 1 millivolt was the voltage that your galvanometer, maximum voltage that your galvanometer could measure for full scale deflection. that is the maximum current that your galvanometer can measure, IG we'll call it, G for galvanometer, times the resistance of the galvanometer. So this is the maximum voltage your galvanometer can handle, divided by the current, maximum current that your galvanometer can handle. So this, you can think of it as a general expression of the resistance that needs to be added in series. But I highly encourage you not to remember this formula. In fact, I would even get rid of this formula. And the reason for that is there are a lot of formulae in physics, and you can't remember all of them. Very easy to get confused and go wrong. So whenever numericals are asked, yes, formula would be easy, faster to do it, but this is a more conceptual way to do it. I don't remember the formula, seriously. I will always try to do it this way. And also, if the questions are very twisted, if you get a different question, say they will give you an ammeter and ask you to convert it into a voltmeter, right? It suddenly looks like a different question now, but the concept stays the same. And so if you understand the concept, you can solve any numerical. And so if you understand the concept, you can solve any numerical. All right, so to quickly summarize, how did we do this? We first thought of our galvanometer as a tiny voltmeter. We figured out what is the maximum voltage it could measure, 1 millivolt. And then we said, okay, now we need to extend its voltage to 10 volts. Then we said, look, that means when 10 volts comes across this, only 1 millivolt should come across this, our galvanometer. And so the rest of the voltage should come across some resistor. And so that's why we added a resistor in series. And then we figured out what that resistance should be using Ohm's law. So to convert a galvanometer into a voltmeter, add an appropriate resistance in series.